All right, folks. Gonna finish up with just the last of this correlation stuff that we didn't get to in class. When we broke on Wednesday, we had just gone through and talked a little bit about covariance. Remember, covariance is just a raw metric of association, kind of like your sum of squares or variance. Covariance is just a raw measure of the extent to which two variables, x and y, vary with one another. So as x gets bigger, what happens to y? But remember that covariance, while incredibly useful for running some of our analyses, not super good for just face value interpretation of whether or not a covariance is big or small. Again, just one of those raw metrics. But what we talked about is if we go through and standardize that covariance, if we divide our covariance by the product of the standard deviation of x and the standard deviation of y, what we get is a Pearson product moment correlation. So this is our Pearson correlation. Remember, this is bounded, a coefficient that's bounded by -1 and 1. Characteristics of our correlation, both the magnitude, the actual number, and then the sign. As our correlations get closer to 1 and -1, indicates a much stronger association. As those estimates get closer to 0, indicating a weaker relationship. And if it's 0, it suggests no association at all. Okay, so again, most of you probably familiar with correlations, how to interpret those, seeing what those mean. And then we finished off last class noting that our Pearson moment correlation is not an unbiased estimate of the population parameter rho. That's that small p, that's just a Greek rho. That's the notation that we use for the population correlation. And we know that our Pearson correlation is positively biased, particularly at small sample sizes. And so when our samples are really small, what we should expect is that any correlation that we estimate from a sample is probably too big, right? And the size of that bias is proportional to the sample size. So what we can do if we're concerned about overestimating that population value and we have a very small sample, what we can do is we can run an adjustment. And so again, we have the formula down here. Adjusted R is just taking our correlation that we estimated and running it through this correction factor. What will happen is this will turn into an increasingly small correction as your sample size increases. So, the question is like, oh, how small is too small? I don't know. It's tough to tell, right? What I would recommend if you're kind of in that ambiguous area, if you have a sample of 15 or 20 or something like that, it probably makes sense to run this. If you're, 30, 40 or something like that, and you want to go through and calculate an adjusted R, compare it with your Pearson correlation and see if there's a big difference. If there's not, wouldn't worry about it too much. Okay. So, talked about how we what our Pearson correlation is, how we go through and calculate that. But oftentimes for null hypothesis testing, we want to get some evidence to see, assuming that the null hypothesis is true, assuming the population correlation is 0, what's the likelihood of obtaining an estimate of with a sample this size of this magnitude or higher, right? Remember, that going back to our hypothesis testing, it's always assuming that the null is true, what's the likelihood of the data? Okay, so here our null hypotheses for our test of our correlation coefficient is that rho equals 0. The association of the population, the association of whatever it is that we're looking at in the population is 0. We can also talk about this as x and y being linearly independent within the larger population. Okay, we're saying that whatever you score on x has no relation to what you get on y. Those two things are independent of one another. Okay, our alternative hypotheses for correlation, rho not equal to 0. Okay, this is just saying that the association in the population is some value other than 0. It's just not exactly 0. It's either something positive or negative. Again, with our non-directional test, it can be either way. Basically, what we're saying here is that x and y hold some form of linear relation within the larger population. Again, remember that when we're talking about our generalized linear model and our correlations, we're always looking at linear associations. Okay. Now to test, to get a p-value, right? To go through and run a null hypothesis test, pretty straightforward and easy with our Pearson correlation. The sampling distribution of our correlation coefficient given the null hypotheses is just going to follow a t distribution with n minus 2 degrees of freedom. Okay, so the t distribution that we know and love that we worked with all last semester, Pearson correlation is tested on a t statistic. Okay, to calculate a t statistic for a Pearson correlation, we've got our formula right here. It's just our coefficient times the number of people in our sample minus 2, square root of that, over the square root of 1 minus our Pearson coefficient squared. Okay, pretty quick, easy to go through, calculate that t statistic, and then we just calculate that t statistic against a critical t with n minus 2 degrees of freedom. Again, this is the same, it's essentially the same thing as an independent sample t-test in terms of getting your critical value and going through and running your test. So when we're just talking about the Pearson correlation and running our actual inference test, easy. It's a distribution you've all familiar with, just a t, and pretty easy to get to our test statistic based on our coefficient here. Okay. Other thing that's important to note is that our Pearson correlation also doubles as a measure of effect size. Okay, so it's kind of our statistic, but it's also just a raw measure of effect, indicating the estimate of this magnitude of an association within the population. Okay, Cohen benchmarks for interpreting small, medium, and large correlations R equal 0.1, R equal 0.3, R equal 0.5. These are just kind of very, very broad conventional benchmarks, but remember that the magnitude of the association or the magnitude of effect is always going to depend on context. There's going to be some situations where a correlation of 0.1 might be pretty impressive, right? And we might kind of make a big deal about that. So use these as guidelines, but also always wanting to have in your interpretations some additional justification consideration for sort of what the context is of this. It's fine to go through and talk about this, but never just tell me like, oh, it's a small effect, a large effect, something like that, without sort of thinking more carefully about things. Okay. The other thing that's pretty cool, we have a straightforward relation between our Pearson correlation and our Cohen's D, our D family of statistics that we used all last semester. Okay. If I have a Pearson correlation, I can turn that Pearson correlation into a D statistic just using this formula right here. 2 times R over the square root of 1 minus R squared will give me a D effect size. Alternatively, if I have a D, I can turn that into a Pearson R, take the D over the square root of D squared plus 4. We'll go back and forth. Okay, and really the only thing that determines which one of these metrics that you want to use is kind of the research question at hand. If you want to talk about, and oftentimes you will, if we're looking at the relation between two continuous variables, R is just a nice way to talk about this because we can talk about the association between X and Y, right? There looks to be a medium to large size effect, or medium-large magnitude association between X and Y based on our estimates in these data, right? We're just talking about an association. But if we have a situation where we're actually looking at the association between a dichotomous indicator and a continuous outcome, that's essentially a t-test, right? And here, even though we calculate a correlation, we might want to convert that correlation into a D statistic if we're if that helps us, if we want to talk about things in terms of standard deviation difference between those two groups. Okay, so again, really emphasized last semester, whenever you see a D statistic, you should be interpreting it in terms of standard deviation difference between two groups. But if we wanted to go through, use GLM language and talk about that not as a mean difference, but in terms of an association, we can move back and forth between these very easily. So again, our benchmarks for small, medium, large D coefficient, right? And this includes hedges G, glasses delta, sort of that whole D family of statistics, but we can move back and forth depending on our purposes, right? So if you're reading a study and they've reported a Cohen's D, and you're interested in sort of doing some sort of a meta-analysis where everything else, all the other effect sizes you have are R Pearson correlations or R coefficients, you can go through and move back and forth with that really easily. Okay. All right. Other thing to think about in terms of, and to note in terms of effect sizes, other thing that we can do with R, if we take R and square it, this turns it into a different index that has some nice interpretability. We square that Pearson correlation, and that tells me the proportion of variability in Y that's shared with variability in X. Sometimes you'll hear this say the proportion of variability in Y attributable to X. That's fine. You can say that if you want. It sort of starts to infer some causality, but I'm not going to get too worked up over that piece of things. Basically, this is just an R squared statistic, and so if I have a correlation of 0.5, right? And I go through and square that, that's going to give me an R squared of 0.25. And what that's going to tell me is that about 25% of the variability in Y appears to be shared with variability in X. Okay. And so those of you with an existing background in regression can start to think about this in terms of a multiple R. When we get into multiple regression, we'll have more predictors, and so we'll have a model R squared. But just for your bivariate correlations, easy enough to take that Pearson correlation, square it, and that's just telling you the proportion of variability in X and Y that's shared across those two. And then again, small, medium, large effects. Again, standardized benchmarks, but please always take into context the research question, method, and things along those lines when you're making interpretations with this. All right, want to talk about a couple quick assumptions with our Pearson correlation. Remember, with our Pearson correlation, our Pearson model is specific to situations where we're looking at the association of random variable X with random variable Y. Okay, remember we talked about a random variable is a variable we generally think about, right? I go through, I collect a sample, I measure something, that's a random variable. Okay, and so what we're looking at is random variable X, random variable Y, but in terms of making sure that my inferences regarding that Pearson correlation is an estimate of the population coefficient, our basic assumption is that our variables are sampled from a bivariate normal distribution. Okay, now we spent a lot of class time last semester talking about univariate distributions, right? This is just, hey, I've got a variable I've collected, what's the distribution of this variable? I've got this other variable, what's the distribution of that variable? If we're talking about a bivariate normal distribution, what we've got is a joint, the distribution of these two variables together, okay? And if we plot this in three-dimensional space, we get kind of a grid or a mesh that might look something like this, okay? Where you can see we've got this ridge that suggests a correlation of X and Y, okay? So this is what this bivariate normal distribution would look like in bivariate space, or in three-dimensional space. Some properties to keep in mind with the bivariate normal distribution, some assumptions, okay? Our assumption for something to meet criteria for a bivariate normal distribution, first thing that we're going to be concerned about is making sure that the marginal distribution of X and the marginal distribution of Y is normal, okay? Now, when we're talking about marginal distributions, just translate in your head as univariate distribution, okay? If I'm looking at the association between extroversion and social support, okay? Extroversion and social support. We would expect extroversion and social support to be associated with one another potentially positively, right? If I'm looking at the marginal distribution of X and Y, what I'm saying is if I look at if I just look at my data and look at the distribution of extroversion, the distribution of extroversion is normal, or reasonably approximates normality, right? And if I look at the distribution of my social support scores, the distribution of my social support scores is normal, okay? These are what we technically would call marginal distributions. For the whole sample, distribution of X is normal, distribution of Y is normal, Okay. So this is nothing different than the distributions that we've already looked at. Where things get tricky is we also have assumptions not just on the marginal distribution, but also on the conditional distribution of x and y. Conditional distribution of x and y says not for the whole sample, but for, if we're talking about the conditional distribution of x, we're saying that the distribution of x values for any given value of y is normal. Okay. So if we're looking at the association of extroversion, which we'll call our x variable, and social support, which is our y variable, right? On my social support measure, let's pick a value. Let's say a value of 10, okay? If I were to just look at all people who had a value of social support at 10 and were to look at the distribution and just get rid of everybody else and only look at the set of scores where someone had scored a value of 10 on social support, what I would hope to see is that the distribution of x values for that value of y are still going to be normal. Okay, so if we go back to our bivariate space here and use this line to bisect and think about this, if this is a three-dimensional object and I go through and here I'm saying for y values equal -1. If I go through and I were to take a knife and slice that distribution, what I would see is, looking at the end, is that the distribution of x values still follows that normal curve. Okay, and if I were to go through and slice this here at -0.5, 0, 0.5, 1, no matter where I slice that, for all values of y, the distribution of x continues to be normal. Okay. And then the same thing for the conditional distribution of y. Here we're saying the distribution of y values for any specific value of x is normal. Okay, so again here, if I'm saying if extroversion is my x value or my x variable, social support is my y value, I'm saying for any value of extroversion, corresponding values of social support are going to follow a normal distribution. So here in three-dimensional space, if I bisect this across and I look at the distribution of the cross-section here for x values equal 0, at x equals 0, all my y's are normally distributed. Okay, and so this is the heart and soul of a couple of different assumptions to qualify a bivariate normal distribution. One are marginal distributions of x and y, just our univariate distributions. If I look at all the scores together, x is normal, y is normal, or at least close. Okay. Conditional distribution, though, then is for any given value of x, all the y's follow a normal distribution. For any given value of y, all the x's follow a normal distribution. Okay, kind of a tricky thing to wrap your head around, but think about this. Let me know, because this is kind of just important. It'll start to get into some stuff that we get into in regression. Now, notice that I've asterisked the distribution, the conditional distribution of y for our Pearson correlation. We're assuming normal conditional distribution of x is normal, conditional distribution of y is normal. Technically, in regression, we have no distributional assumptions for our x values if we've sampled x as a fixed variable. In a classic regression model, we only have distributional assumptions for our outcome variables. Now, if we're going through and we're modeling random predictors, then that changes, but just sort of know that technically for regression, we only have distributional assumptions for our outcome. But for correlation, it's both. Okay. All right. Okay. So here, if we think about this, going back to our grid here and thinking about what this looks like in three-dimensional space. Here we have in three-dimensional space a bivariate normal distribution that's indicating an association between x and y. Question being, just a thought experiment, what would the shape of the bivariate normal distribution be under the null hypothesis? Remember, the null hypothesis says that x and y are linearly independent. If we think about this, if you were to take a bucket of sand and very slowly pour it down onto the ground, what would we get, right? We'd get kind of a cone shape where things would be kind of thin at the top and then kind of spread out circly all the same way in all directions. If this the bivariate normal distribution were reflecting a null association, that's kind of what it would look like. Here we've got kind of a fin shape going on that's indicating a relationship or an association between these two variables. If there is no association between x and y, it all spreads out in the same direction, kind of like again, like just pouring sand down where it all kind of spreads out. So it's would be kind of like a circular kind of sloping cone shape there. Okay, so again, just trying to get you a visual idea for some of this because it can be kind of tricky. Okay. All right, how do we get our Pearson correlation in SPSS? Pretty easy. If you go analyze, correlate, bivariate, will pop up your window here. You just pull in whatever variables you want to run correlations on, and then hit OK. If you ever run into problems, go to your labels tab and make sure that you don't accidentally have a continuous variable specified as a categorical variable or something like that, because sometimes SPSS will balk and not run those if you do that. But pretty easy to go through. Here's your syntax, what that looks like, and then here's your correlation table. We have correlation between my two variables, right? P-value, sample size. Just go through and make sure that you take a look at that and that everything's looking good. Okay. Stata, easy. Here with command is just pwcore and then whatever your variables are, and then if you hit a comma, put sig at the end. That just tells Stata to give you p-values as well. If you add n on the end, it'll give you sample size, right? So again, pwcore, easy way to go through and get your correlations in Stata. All right, so that's our correlation, and that's how we go through and we run our correlation and run our inference test on that, where we can go through and say, okay, do we have evidence for an effect sort of based on data we've collected in the sample? Okay, but we can start to do other things with correlation coefficients, and this starts to increase flexibility in the types of questions that we can ask. One thing we can do is we can compare independent coefficients. Okay, what we're doing here is, let's say I run through and I look at the association of extroversion and social support in college students, and then I want to look at the correlation of extroversion and social support in, let's say, older adults. Okay, and what my question is the association between extroversion and social support, is that equal to the association that we would see in older adults? Okay, and so our null hypothesis is that the population coefficient for the population correlation for population 1 minus the population correlation for population 2 is equal to 0. There's no difference in the population coefficients. Essentially, we're saying row 1 is equal to row 2. Okay. Our alternative hypothesis is that row 1 does not equal row 2. We're saying that the difference in the population coefficients is some non-zero value, again with our non-directional test. We're saying essentially that row 1 is not equal to row 2. What we're saying here functionally is that the association between x and y differs in this group relative to what we would expect in this other group. Okay. Now, if we're tracking this, what you might start to notice, if you have a background in some more advanced models, what we're essentially doing here is running, or sort of the question we're asking is kind of a half-assed moderation question, right? We're saying, does some grouping variable, so does some sort of population variable, does the specific population that we're pulling from, does that change the nature of the association between x and y? Does the relation between x and y differ based on if we're looking at this group versus that group versus some other group, right? Which is functionally a question of moderation, right? So this is one way to go through and take a look at this stuff, but sort of don't ever try and run moderation this way. There are better ways to do it. But again, what we're just looking at here, think about this as an independent sample t-test with correlations, right? Does this group value different than this group value? Okay, is essentially what we're doing, all right? So some cool opportunities with this. Problem is that the formal test is problematic because the distribution of row 1 minus row 2 doesn't follow a nice distribution, right? And remember that in order to have some sort of inference test, we have to know what the distribution of a statistic looks like, and the distribution of row 1 minus row 2 is complicated, okay? So that would say if we went through and looked at the correlation of X and Y in population 1 and looked at the correlation of X and Y in a sample from population 2, and then we subtracted those two values, and then we did that 100,000 times over and over again and plotted out the distribution of those coefficients, the distribution will look kind of wonky. It's hard to predict what that distribution is going to look like, okay? And if we don't know what the distribution is, it's hard to come up with an inference test. So the solution here is what we do is utilize something known as a Fisher's R to Z transform. And what we're doing is we're taking, with Fisher's R to Z, we're taking that Pearson correlation and turning it into a slightly different coefficient, one that behaves a little bit better for us, okay? And so the Fisher's R to Z transform, what we're getting is R prime, okay? It's kind of like you think about this is kind of the Z, we call it R prime. But basically what I'm doing is I'm taking whatever my Pearson correlation is, I take 1 plus my correlation over 1 minus my correlation, divide that, take the absolute value and multiply that by, and take the natural log of that value times 0.5, okay? If I do that, what I'm going to get is a slightly different value, which is going to be my R prime, okay? And R prime now goes through and follows some better properties in terms of distribution. The distribution of R prime is approximately normal around the population prime value with a standard error equal to 1 over the square root of n minus 3, okay? So what we're doing is we're taking our Pearson correlation and we're turning it into a slightly different statistic, a slightly different value, this R prime value, and that R prime value, we know the distribution of that is approximately normal with a standard error equal to this, okay? So what we can do, getting back to our question here, because what we want to do is get an estimate of the difference between row 1 and row 2, okay? So what we can do then, if I want to test this and I want to compare these two associations, what I do first is I calculate R prime for my first correlation, and then I calculate R prime for my second correlation, and then I just plug them into my Z formula. Here we've got R prime 1 minus R prime 2 over the square root of 1 minus n minus 3 for sample 1 plus 1 over n minus 3 for sample 2. Take the square root of that. And again, if you're looking at this formula, this should look really familiar. This is essentially just an independent sample t-test formula. Same type of format, essentially, in terms of the setup. But what this will do is this will give me a Z value that then I can use to test my hypotheses to whether or not I have evidence, reject, fail to reject, null hypotheses in this test. Okay. And again, my Z test is evaluated against a critical Z for alpha. Typically, this is going to be a 0.05. You all know this. 1.96 is our critical value for alpha equal 0.05. Okay. So again, not overly complex. We just have to go through and do some transformations in order to get this. So what I want to do here is compare the correlation in population of X and Y in population 1 against the correlation of X and Y in population 2. I can't do that directly because it gives me a weird distribution, but if I take each one of those correlation coefficients, transform it into R prime, and then use those R prime values to plug it into my Z formula, that'll give me a test so that I can go through and test and make a determination on, assuming that the null hypothesis is true, do I have evidence for some difference in these in these correlation estimates? Okay. All right. This is not something that SPSS will do easily for you. Stata will, Johnny. So if you wanted to use this, all we do here is enter the command cort testy, and then you hit your correlation 1, sample size, correlation 2, sample size, and what it's going to do is it's going to go through, give you your Z statistic, it's going to give you your p-value, you're good to go there. All right. So what we did, again, think about the previous test is just like an independent sample t-test with correlations, right? Does the value for population, do we have evidence of a difference in the value of association of X and Y in population 1 versus population 2, okay? But another thing that happens sometimes is maybe I don't want to go through and make a determination. Maybe my question isn't whether or not R equals 0. Okay, that's kind of our null hypothesis. That's our standard null hypothesis, right, for all of our tests. Anytime you see something that someone's reporting that something's statistically significant, it just means that we have evidence that something's not 0, right? So again, baseline model, our null hypothesis is that rho is equal to 0, the population coefficient is equal to 0. But we don't have to stick to that. Maybe I have a question that says, well, what I'm really interested in is not whether my population coefficient is equal to 0. Maybe my question is do I have, what I want to know is whether or not my correlation between X and Y is different from a value of, say, 0.2. Okay. Basically, let's say I have some sort of question where I'm saying that, in order for the correlation of X and Y to really be meaningful to me, I don't really care if it's not 0, because that's not a reason. I don't care about 0. But what I really want to know is whether or not this is greater than a value of 0.2. Okay? Easy to go through and do this. Okay? Here what we're doing is we're saying my null hypothesis now isn't that rho is equal to 0. My null hypothesis is that rho is equal to some specific point estimate. Here we're calling it capital R. Okay. So again, in this hypothetical example, we're saying my null hypothesis is that rho is equal to 0.2. Okay. And then my alternate hypothesis is that rho is equal to some value that's not 0.2. Okay, so again, if you're thinking back at this, you can kind of think about this as similar to a single sample t-test, right? Remember our single sample test, we were testing whether or not some sample value was equal to, we had evidence that it was different than some reference value that we had specified. Same thing here, we're just specifying a value for the correlation, something that's not 0, okay? How we'll go through this talks about this. Questions the extent to which this is, useful. Essentially what you're doing is calling your shot, though, and going back and thinking about sort of that meal example that we talked about, right, where talk about hard sciences, the difference between calling your shot and testing against some specific point estimate versus just saying that something is likely not 0. This is kind of getting into some of that idea here. Okay, so pretty easy to do. All we need to do here in order to run this analysis, again, we're just using our R to Z statistic. So what I would do is I'm going to take R prime, so whatever my observed correlation is from my data, transform that into R prime, and then I'm going to do the same thing for whatever the point estimate that I'm testing against under the null. Okay, so if I say 0.2, what I would do is I would take 0.2 and run a Fisher's R to Z and sort of transform that, calculate the difference between those values over 1 over n minus 3, and now I've got a Z statistic that I can go through and test that. Okay, so previous example, testing whether or not two correlations from different populations are different from one another. Here, what we're doing is we're just hijacking the mechanisms of this to determine whether or not we have evidence for that our correlation that we've observed in our data is different from some value that's not 0. Okay. All right. Other thing that we can do, and this is maybe the thing that comes up more often than not, particularly with measurement types of things. What we can also do is we can start to run tests of correlated correlation coefficients. Okay. In this situation, what we're typically doing is what we're wanting to do is within a single sample, look at whether or not the correlation, whether two correlations are similar that involve some common measure. Okay, so let's say that I have, I'm looking at, going back to what we had talked about, let's say I collect a sample of undergraduates and I look at the correlation of extroversion and social support, but then I also have a measure of neuroticism. And what I want to do, and my question is the association between extroversion and social support similar to the correlation of neuroticism and social support? Okay, here we've got a different situation where we've got two correlations that we want to compare. But the tricky thing here is that those two correlations, they're all coming from the same data set and they share a common measure, right? Here, my null hypothesis is that the population association between extroversion and social support is different than the population correlation between neuroticism and social support and neuroticism. So we'll say social support and extroversion, social support and neuroticism. Okay, and the tricky thing that happens here is what we've done is we've got dependency between those two coefficients. They're not independent. They're not looking at X and Y in this population and this population. It's all in the same group, but what we're wanting to see is the correlation of X or Y with this measure different than the correlation of Y with this other measure. Okay. So again, our null hypothesis is that rho xy minus rho xz is equal to 0. Difference in the population coefficient of x given y and x given z is equal to 0. We're saying that the correlation, the association of x and y is equal to the association of x and z here with our null hypotheses. Our alternative hypothesis is that there's some difference, right? That the magnitude of the association between x and y is different than the magnitude of the association of x and z within the population. We're saying that these correlations are not equal to one another, okay? And so this is typically the type of situation where we'll see this a lot of times if you're looking at psychometric research where I'm looking at convergent and discriminant validity. I'm saying that my measure of interest should be demonstrate a stronger correlation with this measure than that measure. These types of things is where this can come up. Now, note that the tests of dependent correlations can also involve a comparison of X and Y at time 1 with a correlation of X and Y at time 2. Here we've got kind of a repeated measures thing. This is also a situation where you have dependency. You don't have a third measure here. You're just looking at X and Y at time 1 with this sample and X and Y at time 2 in this sample. Here you would use a similar procedure for comparing correlated correlation coefficients in this situation. Going through and running these calculations, a little bit more involved than the stuff that we've done before, but procedures are outlined in the Howell text, that Steiger paper that was assigned, and then the Meng paper. The Meng paper is really nice because it starts to give you options for other things that you can start to do with this that are pretty cool. So make sure that you go through, read those carefully, and help get your mind wrapped around kind of what's going on here. But let me know if you have questions. All right. Other thing we can do, confidence bounds, right? Love confidence bounds. Can calculate confidence bounds for my regression or my correlation coefficient, which functionally is generated confidence bounds around my effect size. Okay. Now, when we're thinking about doing this, remember that because I can get a standard error for R prime, right? My Fisher's R to Z. This also helps me calculate a confidence interval around my correlation, okay? And because my Pearson correlation also serves as an effect size, what we're essentially doing is calculating a confidence bound around an interval estimate for plausible population values of an effect, okay? Now, the formula for this confidence interval around my population effect here, specifically rho prime, is going to be equal to R prime, so my Fisher's R to Z transform, plus or minus my Z statistic for whatever interval bound that I'm looking for. If this is 0.05 or 95% confidence bound, it's going to be 1.96. If it's 99, it's 2.58, 99.9 with 3.29, right? So basically what we're doing here is we're calculating a confidence bound around R prime, okay? Now the problem is that we're not interested really in R prime. R prime is just a means to an end. So if I just calculate the confidence bound around R prime, I'm not quite there yet. What I need to do is then take that upper and lower bound that I got for the upper and lower for R prime, and what I need to do is back translate that into a Pearson correlation. But this is easy enough because I can back transform my Fisher's R to Z back into a Pearson correlation by taking base E. Remember, this is 2.1. This is just a constant, right? To the 2 times the R prime power, have that value minus 1, divide that by base E to 2 times R prime plus 1. We're just going back through, dividing those two things, and basically what this is doing is it's taking me from my R prime value back to my original Pearson correlation, okay? So because I have a standard error for R prime, I can very quickly and easily calculate a confidence bound around R prime. But R prime isn't a statistic that's interpretable that I want to use. What I want to do is I want to get that back to a Pearson correlation. And so what I do is I just calculate my lower bound, my upper bound, and then take both of those values and run them through this formula. So I would take my lower bound, run it through this to get a lower bound for R, take this value, run it through this, get an upper bound for R, and then I've got my correlation, my confidence bounds around my correlations. Okay, so again, here we're just using that Pearson R to Z transform. Now, to get confidence intervals for correlations in SPSS, we can go through and use this. If we go to Analyze, Correlate, and then we choose Bivariate with confidence intervals, it's going to pop up a window. We just throw in whatever my variables are, tell it what level of confidence bounds, different versions of this that we can go through and get. We'll just go through and use Fisher because that's what we just talked about, and go through and hit OK. And what this is going to do is now it's going to give me the correlation between my two measures. Here's my correlation, sample size, lower bound, upper bound. Okay, same thing here, correlation, sample size, lower bound, upper bound. Okay. We can also do this a couple of different ways in Stata. If I go through and I just run my PW core between my two variables, I get my point estimate here. What I can then do is I can run CI2, variable 1, variable 2, comma core, and then that's going to go through and it's going to give me my point estimate, number of observations, and my confidence bound. Other thing that I can do here is if I don't have actual data, if I just have values, I can use this CII2 to just go through and calculate this manually. Here, what I'm doing is I'm telling Stata to go through and read off of my data. It's saying, hey, estimate the correlation between this variable and this variable and give me a confidence bound for that. Or if I'm reading a paper, I can just open up Stata and I want to get a confidence bound around some correlation that I've seen reported in the text. All I need to do is enter CII2, sample size, enter the correlation, and then hit core. And what it's going to do is it's going to go through and just run the analyses for me. Okay, so a little bit easier with SPSS. You need to have the actual data for it to go through and read. Here you can just plug in values and calculate correlation or confidence bounds around whatever estimate you want to, so long as you know what the estimate is and the sample size. So pretty slick function there. All right. Power analyses. Again, G-Power is a pretty slick way to go through and do this. Pretty simple, straightforward. What we're going to do to get a power analysis for some correlation we're wanting to power a study for, we go to open up G-Power, and under test family, choose exact, and then select correlation bivariate normal model. Okay, and then you just go through and do the stuff that you would normally do, right? So you say two-tailed test. We're wanting to see what sample size we need to have adequate power to detect a correlation of 0.3. alpha is 0.05, power 0.8. The null correlation, we're assuming so that the population, the null value is 0. Go through and hit calculate. And this is saying that we would need, in order to have adequate power to detect a correlation of 0.3, we need about 85 people in a sample. Okay. So again, pretty slick, pretty quick and easy to go through and run your power analysis in GPower. All right. So that's our Pearson correlation, right? This is our bivariate normal correlation. To this point, what we're assuming is that we have continuous random variable X and continuous random variable Y, okay? But there are other versions of correlations where we're looking at the association between two variables that don't necessarily have to be continuous, okay? And one of these is going to be a point by serial correlation, okay? The point by serial correlation is a formal test of an association between a dichotomous X value and a continuous Y outcome, okay? So if I've got a situation where I want to run a correlation between a dichotomous indicator, a 0-1 indicator, and some continuous outcome, technically what I'm running is a point by serial correlation. But the nice thing is your point by serial correlation is mathematically identical to your Pearson correlation. Okay, they're 100%. They're the same thing. You don't have to go through and change anything in the calculation of these. Okay. Now, if I'm going through and I'm actually plotting this out and run a scatter plot and look at what this looks like, it doesn't look like the nice correlation stuff that we've gone through before. Okay. What we do is what we see is basically what we're doing is we're drawing a sort of plotting a line that's looking at the point where when my X value is 0, capturing the mean of my Y for cases where X is equal to 0, and when X is equal to 1, we're drawing a line through the mean of group 1 here, and basically just looking at the association or the line between these two groups. Okay. So if I go through and I take that point by serial correlation and I square that, again, that's still giving me the proportion of variability in Y attributable to variability in X or shared with variability in X. The coefficient works the identical same way as a Pearson correlation. We just call it a point by serial correlation if we have a dichotomous X and a continuous outcome Y. Okay. Now, if you're thinking about this, you're like, okay, well, wait a minute. When I have a dichotomous X and a continuous Y, all last semester what we did is we ran those with t-tests, right? This is our independent sample t-test, right? Well, what we see is that our significance test or our inference test for a point by serial correlation is identical to the same process that we used for our t-test for R, okay? So here we just have our point by serial times the square root of n minus 2 over square root of 1 minus the square of my point by serial correlation, still evaluated against a critical t of n minus 2, okay? And what we see here is this is the point by serial correlation that has a is mathematically identical or sort of functionally identical to our independent sample t-test. If I calculate my point by serial correlation, this is going to be equal to my independent sample t-test. If I take my test statistic squared over the square of my test statistic plus the degrees of freedom, this gives me a point by serial correlation. Okay, so what I can do is, as a consequence of this, is that my point by serial correlation and my means-based test, these are interchangeable. Okay, anytime I'm running a t-test, an independent sample t-test, I can represent this as a point by serial correlation. Anytime I have a point by serial correlation, I can represent this as a means-based test. I can move back and forth with these. The only thing that makes a difference is how I want to talk about it, right? So I can talk about men and women differing in weight on average, right? We say on average, men have greater mass than women, right? That's kind of a t-test, kind of like a group-based analysis, right? But I can also talk about this as saying there's a linear relation between sex and weight, Okay, I can say that sort of men, the population of the average mass in the population of men is different than the average mass in the population of women, right? Talking about this in terms of mean-based tests, or I can go through and I can say that sex and weight are associated in the population, right? I can also talk about physical weight varying with sex or gender, right? Depending on sort of what I'm my target question, what I'm measuring. All of these are 100% appropriate and okay ways to go through and talk about things. It just sort of gives you some flexibility to start framing things in ways that are most consistent with however you want to go through and talk about them. Okay. So again, point by serial correlation in my SPSS output, there's not a specific command for point by serial correlations. You just run the correlation like you would normally do. You would just drop in your categorical, your dichotomous predictor, and your continuous outcome, and you just run those, right? And so if I do this, if I look at the association in these data between sex and PTSD scores, right? This is giving me my correlation, my p-value, sample size. If I were to go through and run these same data as a t-test, where I'm looking at mean differences in PTSD scores across men and women, what I'm going to go through and I'm going to see that my p-value that I got here for my correlation is identical to the p-value that I get for my t-statistic. Okay. Now we get different types of ways that we get different metrics that we can talk about this differently. Here I'm just talking about the association between sex and PTSD, right? Here what I can talk about this in terms of there's a mean difference of about 2.2 points. Here's my lower bound. Here's my upper bound for population, reasonable population values given the data, right? But mathematically, it's all the same thing. It's all capturing the same association. The only thing that differs is how you want to talk about it. Okay. Same thing in Stata. If I go through and I use my PW core to look at the association here, and then I run it as a t-test, again, my p-values are identical because they're mathematically functionally identical tests. All right. So again, we already know this. We know that Pearson correlations have a direct association with Cohen's D. Same thing with our point by serial correlation. It's just with our point by serial correlation now. What we can do is that D statistic makes a little bit more sense if we've calculated a point by serial correlation, if we've got a dichotomous indicator and a continuous outcome. Okay. And then what we can do is use that our confidence intervals we can use our t-statistic from our point by serial correlation to then go through and back calculate confidence bounds around D using those procedures that we used last time, right? So conceivably what I could do is I could calculate a point by serial correlation, right? And calculate a test statistic, a t-value for that point by serial. But then what I could do is I could take that point by serial, turn it back into a D metric because maybe I want to talk about it as sort of a standard deviation difference. I get an estimate for D, and then what I can do is take the t-value that I got for my test of my point by serial, run that through my Steiger software, and use that output to calculate the upper lower bounds from D based on the information I've got. Okay. So again, this is all just the same stuff that we did last semester. All right. But what's cool is if I go through, let's say, you're reading a paper, and what the paper does is it just reports a correlation between some dichotomous indicator and a continuous outcome, right? And that's all they gave you. They gave you that in sample size. But what you really want to do is you're wanting to run a study using a t-test and a sort of a group-based analysis. What you can do with just that correlation and that sample size is you can back translate that. You can use that to go through and you can use that to calculate a D statistic. And then you can use that value to generate a test statistic for that. Use that test statistic to get an upper and lower bound for the D. And now you've got a whole different set of metrics that are functionally equivalent, but something more similar to what you might want to use. Okay. And so this is where things really start to get cool, is when you can dig into published research and start taking the numbers that they give you and turn them into stuff that's more useful for you, okay? And so as long as you see the relations between these and recognize those, a lot of cool stuff that you can do with this. Okay. All right. Last thing we're going to talk about is a phi coefficient, okay? Phi coefficient is a test of the formal relation between a dichotomous X and a dichotomous Y, okay? Our phi coefficient, again, though, is functionally mathematically equivalent to, again, my Pearson correlation. So anytime you have any combination of continuous or dichotomous variables, you can go through and run a Pearson correlation with that. That's perfectly legal. If we've got a dichotomous X and a dichotomous Y, we technically call it a phi coefficient. If we've got a dichotomous X and a continuous outcome and a continuous Y, we call it a point biserial. But it's all mathematically equivalent. It's all the same thing, okay? Now, what we know about the phi coefficient is that has the distribution of our phi coefficient follows a chi-square distribution with 1 degree of freedom, so that my phi coefficient is equal to a chi-squared over the my sample size. Take the square root of that. That's going to give me a phi coefficient, okay? So just like our Pearson point biserial and our t-statistic were interchangeable, my phi coefficient and my 2 by 2 chi-square are interchangeable, okay? So normally if I had dichotomous X and a dichotomous Y, I might use a chi-square to go through and look at the dependence of those two variables, right? Or I can just dump it in and calculate a Pearson correlation. Technically it's going to be called a phi coefficient, but basically I can move back and forth with that chi-square, get a phi, again, can move interchangeably back and forth between these, okay? So again, I can talk about this in terms of the association between a dichotomous X, dichotomous Y, if I'm talking about things in terms of my phi coefficient, or if I want to talk about things in terms of my chi-square test, I can talk about a test of independence between my dichotomous X and dichotomous Y, right? Does defendant minority status hold an association with death penalty verdict or something like that, right? So I've got a dichotomous predictor, a dichotomous outcome, and then I'm looking at the association between, is there an association between those two? I can represent that as a chi-square test, or I could represent it as a phi coefficient. Phi coefficient is nice because that's actually more interpretable, because I can just interpret that like I would any other Pearson correlation. Okay, so again, if I go through and I'm looking at the association between participant sex and PTSD diagnosis, no, yes. If I go through and I run this using a chi-square test, I see that my p-value for that test is 0.79. My phi coefficient is negative 0.01. If I were to take these two variables and just run a correlation with them, I get the same correlation. Okay, I get the almost identical p-value here. These two things are functionally interchangeable. Okay, same thing with Stata here. If I run PW core, if I look at the relation between sex and diagnosis here, I'm getting my correlation. If I go down here and I run a chi-square, tab gender, caps dx for my chi2, it's giving me my Pearson coefficient and my p-value. We're seeing that the p-value is identical across those. Okay. All right. So what we went through and talked about is we talked about our Pearson correlation, right, which we generally are thinking about a continuous X, a continuous Y. Our point biserial correlation, which is a dichotomous predictor X and a continuous Y, or my phi coefficient, which is a dichotomous X and a dichotomous Y. All of these situations are all mathematically equivalent. So anytime I have any combination of two variables that are dichotomous or continuous, that's all sort of covered under my Pearson correlation. Okay, but there are going to be other situations where we go through and we have correlate or sort of distributions of levels of measurement that don't necessarily sort of fit quite in there. And what we have is we have different correlation coefficients for those cases. So, and these is not an exhaustive list, but for some examples, a biserial correlation, similar to my point biserial, but here what we're doing is we're assuming continuity in the dichotomous X. So what we're doing, if I have a situation where I've got some variable that's coded as high, low, or something like that, but I know that the construct is continuous underneath, right? So let's say my variable is a guilty, not guilty decision, but I really know that guilty, not guilty, the underlying dimension is some continuous dimension of certainty of guilt, right? Where at some point we just say, okay, yeah, it's got to a point where I say, yeah, guilty versus not guilty. If I wanted to recognize that even though I have a dichotomous X value, the underlying sort of construct is likely continuous, what I could do is estimate that with a biserial correlation, okay? And what that's going to do is it's going to treat that underlying dimension as continuous and sort of recognizing that my physical representation of that is a yes-no variable or a 0-1 variable, but it's sort of changing the estimation to assume that the underlying dimension between that dichotomy is actually continuous, okay? Tetrachoric correlation, this is similar to a phi, but here we're assuming underlying continuity with both our x and our y. So what we've actually done is we've measured 0-1 variables, but what we think is that like those 0-1 variables are actually just sort of points on an actual continuum. A tetrachoric correlation would have specific and unique ways of estimating that to account for that underlying continuity. Okay, Spearman's rho. This is a version of a Pearson formula to ranked scores. Okay, if my data aren't truly continuous, if it's an ordinal ranked score where people are ranked 1, 2, 3, 4, 5, 6, what we're looking at is changing this over and using a rho. Kendall's tau. This is a different way to look at associations between ranked scores. A little bit better estimate than Spearman rho. Has a known standard error that's sort of helpful. We've got different squared tests of linearity with ordered categorical data. We've got a Kendall coefficient. This is if we're using ranked data and we're having people rank these, okay? So again, you don't have to worry necessarily about these. These start to get into some more niche areas and sort of some stuff that dips back into our history a little bit, where some non-parametric stuff was a little bit more common. But just knowing that if I'm looking for an association between two variables, the level of measurement really starts to determine what form of that association I'm going to go through and use, okay? So Pearson's the big one, right? And anytime we have any combination of continuous or dichotomous variables, Pearson correlation is going to be fine. But if you're finding you're doing research that kind of deviates out, there are some other options available, okay? All right, that's it. Thank you so much, folks. Go through, take a look at this. Make sure that you don't have any questions. If you do, come talk to me. Make sure you got readings done for this first set. Doing those ahead of time will help you immensely, as opposed to jumping right in. Then you're going to just spend a lot of time being confused and spinning circles. So make sure you do the reading, take good notes, make sure you got to understand that. And if you do that, the stuff should come together pretty quickly on this first set. So again, thanks for your patience. Excited to get the semester started, and let me know if you run into hiccups. All right, thanks.